Hello and welcome to the lecture. This is going to be a short lecture to complement the solution to test 1 that is already posted. But I just want to give you a brief introduction to Simulink and to talk about what Simulink is and how it's used. So Simulink is a component of MATLAB and is extremely useful to really handling complex systems. So we'll start with the introduction and see how it's used and the main components of that application. So let me start here. Right. So you see my screen, and just get here. Okay. All right. So we introduced in Simulink, which is a MATLAB component, like I said. And Simulink is part of many other components in MATLAB. MATLAB has just about any sort of application, any sort of component for just any scientific application you can think of, any engineering application you can think of. But some of those components are sold separately, okay? They're used, depending on what the application is in your area. But Simulink comes with MATLAB and is one of those components. But Simulink uses a graphical user interface so that you can easily model systems. It's especially useful for modeling dynamic systems, those that can be described by differential equations, but not exclusively for that, but the major impact is on systems that can be solved through differential equations, but it can be used just for about any other kind of system. It relies on a large library of blocks, which can be combined to, solve many kind of problems. It's very visually, and it's different than building programs or code in MATLAB, which MATLAB depends on individual M-file components. But the approach for Simulink is more visual, as you'll see in a minute. You construct or develop Simulink models by building a diagram that shows the elements of the problem to be solved. These diagrams are called simulation diagrams or block diagrams. So when you use Simulink, you need to create a model. And you create a model by using blocks, similar to making block diagrams. Blocks are copied from libraries and connected manually. You'll see how those libraries work. It contains parameters that can be fixed or changed. Some parameters can be changed during simulations. And there are two main types of block libraries: standard Simulink libraries and user-defined libraries, which also makes this a very powerful component, because you can also create your own libraries. If you create a model of a system, you can just save it and reuse it as you please, because you can recreate your own. So let's look quickly at a simple example so we can start kind of getting an idea of where this leads to. This example here, we have an equation. It's a differential equation. It says that the derivative of y is equal to 10 times a function of t, 10 f of t. So solving that differential equation is not difficult, even if you haven't taken differential equation, because all you got to do, if you integrate both sides of that expression, on the left-hand side, you get back y, because integrating a differential will give you back the function, right? And the integral on the right-hand side, you can see then is 10 times f of t dt. Well, this can be thought of as two steps, right? Using an intermediate variable x of t, we call x of t equals 10 f of t. We can replace this expression here by this one, by using x of t representing 10f of t. And so if we try to do that graphically, you can easily see that it really consists of two blocks, if you think about it, right? It can be represented graphically in this simulation diagram by showing, first of all, that you have a gain, right? This represents a gain of 10 and a derivative followed by a derivation. So, which is what this expression is telling you, right? Is taking your function f of t, right? F of t is here, is multiplying it by a gain of 10. This 10 block represents a gain of 10. The output of that multiplication, 10 times f of t, is this x right here, right? And then that x is then taken through an integration process, which is represented by this block, which gives us the output. So the arrows represents the variable x, y, and f, and the block represents what is called the cause and effect process. The first block producing a gain of 10, and the second block implementing an integration function, right? So you can see right here that we quickly and easily can represent this mathematical expression by this block diagram, right? And so understanding how we go from this equation to this block diagram is important, right? But you can see it's not that difficult to interpret. And so going back again to the block diagram, we generated a simulation diagram. The block contained in the number 10 represents this process, right? 10 times f of t, where in this case, f of t is the cause, the input, and x of t represents the effect or the output of that block. This type of block is called a multiplier or just a gain block. Either name is okay. The block containing the integral sign represents the integration process, or y of t equals the integral of x of t dt, where again, x of t is the cause, the input, and y of t represents the effect or the output. This type of block is, for obvious reasons, called the integrator block. Okay. Now, we could have also done or come up with a similar solution by looking at another method that is called Laplace transforms. Now, you don't have to know Laplace transform for this. I'm just going to give you the result of using Laplace transform, and you'll see that it become obvious, but it's not necessary for you to know how Laplace transforms work. But if you take the original equation, which is the derivative of y equals 10f of t, if we take the Laplace transform of that expression, which at this point, don't worry about that. We're just going to take it for granted that we have the same derivative represented by this Laplace transform, which gives us another form, okay? And you'll see that in a minute. But anyhow, if we take the Laplace transform of that equation, we get an expression that is says s times y is equal to 10f, and which gives us the solution here, right? So the solution now is a solution not in the time domain anymore, but it's what is called the frequency domain. Again, don't worry much about the math behind it. What I'm interested in is that you know how to interpret this as a block diagram. And you'll see that in a minute. And what happens is that the integration symbol in the integrator block is really replaced by the operator 1 over s, which derives from the notation that is used for Laplace transform, meaning that if you look back at this, right, the integration in the time domain is represented by the factor 1 over s in this Laplace transform method. So if we now look at, instead of being represented by a box, the multiplication process is now represented by a triangle, which we'll see here at the bottom of the screen. That is used to represent, similar to what we used to represent an amplifier. And that's what it's called a gain block. So using this Laplace transform method, then x is still 10 times f, and y will be x over s, right? Because x is 10f, right? That didn't change. X is still 10 times f, but now y is equal to x over s, right? So again, doing this way, the Laplace transform way, change the representation of the integral in the time domain by just a division by s. Again, don't worry about it. That's not important that you understand that. What's important now is that we came up with a different model. And we can use that model then to solve also for the solution. So let's implement that then using this model now, where this again at the bottom here you see the block diagram, but now the gain is represented by this triangle, and the integration is represented by this factor 1 over s. But the output is going to be the same. We're still looking for the derivative of y equals 10 sine of t, and we're going to take it at initial conditions of 0, and we want to look at the output y over the range of t from 0 to 13. Okay, so again, we want to solve this differential equation at initial conditions of 0, and we want to run it from 0 to 13, and the output is equal to y. Okay, so that's what we want to solve, and we want to solve that differential equation using Simulink. So how do we use Simulink? Well, first of all, to start Simulink, you can simply type Simulink on the command line, or in the command window, or from the home window, you'll see a logo that says Simulink. If you click on that logo, as you'll see in a minute, we'll do that in a minute, you can start running Simulink. And once you do that, you're gonna, one of the things you're gonna do is you're gonna select from a library the components that you're gonna use. And you're gonna see something similar to this, where you're gonna see a bunch of library components, depending on what application you're using. And as you choose on each of those components, you're gonna see elements inside. And you're gonna choose those elements that you're gonna use to build your model. So for instance, in the previous example, for us to solve this problem, I'm gonna need two blocks. I'm gonna need a gain block, and I'm gonna need an integrator block. See, right? A gain block and an integrator block. And I'm gonna choose from the library those blocks, and I'm gonna put them in a workspace. I'm gonna join them together, and then I'm gonna try to see what the solution looks like. So that's the process, right? So let's see now. Sorry. So we're going to look real quick how easy it is to use Simulink to solve the kind of problem we have already selected. And the problem, if you remember, is to solve this differential equation, right? And the way we're going to solve it is by implementing this block, right? So the input function comes in to a gain of 10, or an amplification of 10, and then it goes to an integrator, and then at the output we get the result at the output of the integrator. So we need to implement this model. And so one of the things you do when you first implement models in Simulink is to try to figure out what is it that you need, what are the different components you're going to need. So in this case, I know that I'm going to need a sine function, I'm going to need a gain or an amplifier, and I'm going to need an integrator. And I need something to look at my output. So I'm going to insert at the end here, at the output, I'm going to put a scope so I can see what the output looks like. So let's see how we implement this, right? So to get to Simulink in MATLAB, there are two quick ways. One way is to simply type at the command window, just type Simulink, and it'll bring up the menu for Simulink. The other one is to simply click on the Simulink button here and start Simulink immediately. And you can see here, it brings up this menu for Simulink, where you can create your own project. And as you can see, there's some predefined libraries that come with the system for specific applications, like in DSP, signal processing. You have all kinds of applications, communication, filtering, and so forth. There's also examples if you want to take a look. The examples are a little more advanced, but it gives you a good idea of how powerful this is if you want to take a look at those examples. But in any event, we want to then start with a blank model. So I'm going to click on the blank model here, and as you can see, we created this workspace for me where I'm going to build the system that I want with the different blocks that I want. So to do that, I'm going to start with the this button here, which is the library browser. And the library browser brings up all the components, the different blocks that are available in Simulink for all kinds of applications, like I said before. So I'm going to bring up the main component here of Simulink to grab the different items that I need. And so if you remember, right, based on this, again, I need a sine wave, I need a gain, and I need an integrator, right? So I'm going to select it from here. So I'm going to select a sine wave, and for that, I'm going to go to the sources menu here, and then the sources, I'm going to look for a sine wave. And the sine wave is right here, right? You see it. So I'm going to drag that to the area where I'm going to implement it. As you can see, it gives me the option to put in the value for the emphasis. I can type it in here and then enter it, and it'll save it, or I can double click on the sine block, and I can put the different items that I need. I want an amplitude of 1, a frequency of 1. So I'm going to just leave it like that, and I'm going to select OK. Okay. And the next thing I did, and of course, when you open up Simulink, you have different windows going on. So you got to be, you just got to be aware of, what is it that you have. So I'm going to select now my gain, right? Go back to, I was going to tell you about all the windows you have open. So I need a gain. So for the gain, I'm going to go to the math operations, and you see here I have a gain block that I can use. And there's a bunch of other things that you can do, as you can see. Sum, subtract, and so forth. All kinds of mathematical operations. So I'm going to bring the gain again block to what I needed, and again it tells me what gain do I want. Well, I want a gain of 10, so I'm going to just enter it. Probably didn't take it because I didn't enter it quickly enough. So let me double click on it. I can enter from here. I'm going to select 10 and click OK. All right, and I'm going to set it aside. And the last thing I need is an integrator. Well, one of the last things. So I'm going to go back into my library, and I'm going to look under continuous. I'm going to look for an integrator, and it's the second item from the top. And so I'm going to drag that one. He also, and the last thing I need, and the initial conditions, right? It says initial conditions. Well, I'm going to make sure that the initial conditions are 0, and again, I'm going to enter it. And the last thing I want is a scope so I can see the results. So I'm under sinks here. I'm going to select the scope, and I'm going to again drag it to the area. And all I got to do now is, by the way, this scope you can select different ports if you want, if you need more than one. And I'm going to show you another way of doing this also when when you look at your system. First of all, let's connect the elements, the different blocks first. So again, the order is that I have a sine wave. The sine wave is going to go through a gain, and the gain is going to go to the integrator, and the output of the integrator is what I want to connect, right? So to connect, you simply select, see there's a little arrow at the output of the sine wave. I'm going to connect it to the input of my integrator. Just drag it and let it go when it hits the input, like that. And I want to select the output to my scope, right? And on the scope side, I can then look at, you know, how the signal output is going to look like. We'll see that in a minute. So my system is ready. The only thing I need now is to remember the initial conditions, or the conditions I have is that I want to see the system output from 0 to 13 seconds. I want to change this 10, that is the default, to 13 to see the solution that the problem is asking me to look at. And then I'm just simply going to play this and run it. And when I run it, it's going to bring up the scope. You may not see it here, so you may have to look for it, but you can see it here now. And that's the output, right? As you can see, now I have a signal of amplitude of 10, right? Goes from a gain of a total peak-to-peak value, sorry, 20 volts peak-to-peak. So the amplitude is 10, and that's the output, right? It's a cosine wave, because the input was a sine wave. When you integrate, you get a cosine wave. Now, if I wanted to have multiple if I wanted to look at the output and input at the same time, I'm gonna delete this scope, and as you can see, if I right click on this and click delete, I'm gonna delete it, and I'm gonna bring what's called a floating scope, and I'm gonna hook that up. But the way I'm gonna hook that up is I'm gonna hook that up to the input and to the output, to this sine wave, right? So I'm gonna double click on it, and as you can see under this lock, there's a signal selector icon. I'm going to select on that, and it shows me what do I want to connect to. And I want to connect to the integrator output into the sine wave output, so I can look at both at the same time. And by the way, you see here that I haven't given my project a name yet, okay? But you can do that at any point. So I'm going to close that, and now when I run this, it shows me you can run it from within the scope also, as you can see, or you can run it from within my project. But now you can see my input, right? My input is a sine wave of 1, amplitude of 1, so peak-to-peak value of 2, and my output is a signal of a gain of 10, so it goes from 10, has a peak-to-peak value of plus minus 10, so the total swing is 20, right? And as you can see now, the input is a sine wave, and the output is just the cosine wave, right? And that's it. That's how easy it is to implement something to solve using the block diagrams in Simulink. So now we'll look at another one to see some of the other features we can use. Okay, so we're going to look real quick how easy it is to use Simulink to solve the kind of problem we have already selected. And the problem, if you remember, is to solve this differential equation, right? And sorry, I was repeating that. Let me go and start the new one now. So now we're going to make a change to the model we created to solve the differential equation. And what I want to do is I want to send the output that I'm getting, I want to send it to the workspace. I want to create an output signal that then I can probably use in MATLAB like any other signal I generated before. So first I'm going to get rid of the scope. I'm going to right click on it, and you can click on delete and it'll get rid of that, whatever you want. And then I'm gonna try to send this output to the workspace area. So it creates a variable with a name I'm gonna give it. And I'll also, so let me do that first. And to do that, I'm gonna go to the library and I'm gonna go to the sinks area, which I'm right here. And I'm gonna select or click on to workspace. And it is as it says in here, look, write input to specify time series, array, or structure in a workspace. Okay, so it's sending the output to the workspace in MATLAB and any format that I want, as a time series, as an array, or a structure. Let me bring this into the model here. And I want to connect, or I want to see two signals. I want to see the output signal from the integrator, but I also want to see the output signal from the game itself. So to route two signals into this block, I'm going to use a multiplexer. I'm going to go back to the library, and this time I'm going to go into signal routing, and I'm going to select multiplexer, and I'm going to bring it into the workspace, and I'm going to put it here in the model. I'm going to do two things before I do any connections at this point. I'm going to double click on my workspace block, and I'm going to change the name of the output, the variable I'm going to give it, right? So I'm just going to give it the name y, okay, as a variable name. And I'm also going to select the format. I'm going to save it just as an array. So the output is going to be saved as an array with the name y. And I'll click OK. And then on the multiplexer, I'm going to make sure that I have two inputs into it, okay? Which is what I need. I need one input from the integrator and one input from the game, and that's going to be routed to the workspace. Okay. So to do that, I'm going to click on the output from the multiplexer, bring it into the input to the workspace, and since I need two signals connected, one of course is my integrator, right? So I have that one here, and then let me bring this one. I'm gonna need the output from the game. So I'm gonna use this to connect to my game, as you can see here, right? So I make a connection from the game to the first input of the multiplexer, and for the second input to the multiplexer, I'm gonna bring the output of the integrator. And now I have what I need. I have two input signals into the multiplexer, and the multiplexer is going to route each of those signals into a variable called y. And that variable is going to have two columns. The first column is going to have the gain of this block, this output gain, and the second column is going to have the integrator output. And of course, I have selected the time from the original problem to go from 0 to 13, right? And that's it. I can then run it. And notice here that so far in the workspace, I don't have any variables saved or anything. So I'm going to run this model, and you'll see that now that it's finished, it created the two variables that I was expecting. One is the time information that includes the time interval from 0 to 13 with simulation steps. And the other one is the y, which includes those two signals, the integrator output and the gain output. And if you go and look into those variables, you'll see, if I double click on them, let me move this around so you can see it. You can see the two outputs, right? So this first one is the gain, output of the gain, and the second column will be the output of the integrator. And if you look, let me bring this back here. Okay, and if you double click on the T out signal, or variable rather, it includes the timing information from 0 to 13. You don't see it here, but it goes down to 13, which is the range that I have let me make this smaller. So as you can see now, the range goes from 0 to 13. So that's what this did. It created an output workspace. It puts the output into the workspace of MATLAB or whatever signals I need. And if you plot them, I'm going to plot them now. You can see using this command here, which I already have arranged, so I can plot the two signals. And now you can see both signals from the simulation in Simulink created and used by variables in MATLAB, where I have the output of the gain as red and the output of the integrator as green. Okay. I can also, if I go back to my my Simulink area, I can save this file, and I'm going to save it as a Simulink file with the format, with the extension SLX, and I'm just going to give it example 1. And it's going to say that that's example 1. And so you can see here it's got that name associated with this model. And if I need it again, I can just bring it from wherever place I saved it. Okay. So you can see how simple it is to implement. Right? It's very intuitive. So this is a brief introduction into Simulink. I hope you get a good, feel for what it's used for. But you can see how simple makes it to implement this type of equations and this type of problems. And there's no writing of code or anything, as you can see. Everything is done. Obviously, we can do this same thing. We can solve this same problem using MATLAB code. But this kind of skips that process, but at the same time, you can generate your own data that way. And then you can go into the MATLAB application and use that data for whatever other purposes. Like we did just here, we had two outputs, one from the gain, one from the integrator. And we brought that back into MATLAB and we use it to plot the information. So that's the usefulness of it. So that's all for today.